For thousands of years, ancient cultures worshipped the warmth and light-giving sun as a god. For just as long, inquisitive people looked to the sky and wondered what the sun and stars were, how they worked, and what they were made of. It is only recently that the elements the stars are made of and the processes that fuel them are coming to be understood in the equivalence of mass and energy, and in the processes of nuclear fusion. Today we understand how they generate their heat and light, their life cycles, and that most of the matter around us and that we are made of was formed inside of stars. The process of how the elements which surround us were created inside of stars is called stellar nucleosynthesis. The story of the understanding of stellar nucleosynthesis starts in the early 1900s, where the current understanding of physics had led to two diametrically opposed positions. It was unclear what fuel the sun burned, and calculations suggested that by gravitational pressure and fed by comets and asteroids, a compressing hot ball of gas like a sun would shine for only about 2 to 3 million years. Unfortunately, by 1905, the newly identified radiation that some elements emitted encouraged a new field of radioactive dating, and the evidence which arose suggested that the Earth was at least 1 to 2 billion years old. So how could the Earth be more than 1,000 times older than the Sun? Astronomers were perplexed, but no one knew of any process that could fuel the Sun for that long. In 1920, the physicist Hans Bethe was out on a date with his fiancée when she looked to the starry night and commented on how bright and pretty the shining stars were. Bethe, whose mind was probably not where it should have been at the moment, had been thinking about the new discoveries in nuclear physics, and the fuel needed to power stars for so long, and he realized that it must be nuclear processes which fuel them. Yes, and I am the only one on Earth right now who knows how they shine, he replied, trying to impress her. Unimpressed, she laughed at him and said, "That's nice, dear." But they stayed married for life, so maybe there was something to that. Physicist Hans Bethe and Arthur Eddington showed through calculations that nuclear fusion processes could keep stars shining for billions of years. Stellar nucleosynthesis is the name of the nuclear fusion reactions in stars during their lifetimes and at their catastrophic ends that create the energy which powers the star and synthesizes new larger elements out of the simple small elements which fueled it. To understand the stellar nucleosynthesis process, it's necessary to have an understanding of the reactions involved and the forces which govern those reactions. To do that, we'll do a quick overview of nuclear fusion reactions. After that, take a close look at the proton-proton chain reaction, which is the first few critical phases in the nuclear fusion process that fuels stars. After stars run through the proton-proton chain, they evolve to a different type of star and subsequently go through the carbon-nitrogen-oxygen sequence. As a star reaches the end of its life, it can either fade away or collapse and explode in spectacular events called novae and supernovae. These explosions are fueled by and initiate fusion reactions which create all the heavier elements in the universe. To understand nuclear fusion, we must first look at the structure of the atom. The atom is made up of a nucleus, which is its center or core, and a cloud of particles surrounding it. The nucleus of the atom is made up of only protons and neutrons. These are massive particles compared to the electrons, which surround the nucleus in orbitals. Electrons have a negative charge, protons a positive charge, and neutrons have no electrical charge. Protons and neutrons are often referred to as nucleons, that is, particles of the nucleus. The two primary nuclear processes are fusion and fission. Nuclear fusion is the joining of two smaller elements to make a larger element. Nuclear fission occurs when one larger element splits into two or more smaller ones. Both of these reactions can release tremendous amounts of energy. Nuclear fusion reactions are governed primarily by two forces, the electromagnetic force and the strong nuclear force. The electromagnetic force is the force that charged particles exert on one another. Particles with the same charges repel, while particles with opposite charges attract. The electromagnetic force is effective over very long distances, theoretically infinite, and it is a very strong force, more than a trillion billion times more powerful than gravity. Consider that the electric charge on a comb, with enough of a static charge to hold up a piece of paper, is more powerful than the gravitational pull of every atom of the Earth. The strong nuclear force, however, is much stronger than even the electromagnetic force. It is the strongest force yet identified. It operates only over extremely short distances, and the weak nuclear force also governs some reactions primarily relating to radioactive decay. So how strong is the electromagnetic force? Consider two metal spheres 1 meter apart, which lose electrons and so gain a positive charge of 1 coulomb. The common unit of charge is the coulomb, and 1 coulomb is equal to 6.24 times 10 to the 18th electrons. This is about the same charge that a 100-watt light bulb uses in 1 second. The formula for calculating the force on two charged spheres is simple. It is the charge on sphere 1 times the charge on sphere 2 times the constant which describes the magnitude of the relationship between electric charges, Coulomb's constant, all divided by the distance between the two charges squared. Now, plugging in our numbers, we see that the force equals 9.0 times 10 to the 9th, or Coulomb's constant, times our first sphere's charge of 1 coulomb, times our second sphere's charge of 1 coulomb, divided by the distance between the spheres, or 1 meter. So 9 times 10 to the 9th times 1 divided by 1 squared is equal to 9.0 times 10 to the 9th, or 9 billion newtons. That's about 1 million tons. Now that we have an idea of how strong the electromagnetic force is, let's take a look at the forces present in the nucleus. Protons are positively charged, so they repel as like charges repel, while neutrons have no charge. So if a nucleus is full of positive charges and neutral charges and like charges repel, what holds the nucleus together? It is the strong nuclear force, much stronger than the electromagnetic force, but only over very short distances. Now, let's take a close look at a simple fusion reaction between two nucleons. Two protons near each other are charged particles and can be thought of in the same way as two charged metal spheres. As the protons are brought close together, their electrostatic fields repel. The closer they are, the more they are pushed apart. As they are brought closer together, however, the strong nuclear force, which is attractive, gets stronger and tries to pull them together. If they get close enough, the strong nuclear force exceeds the electrostatic force, and the protons are suddenly pulled together. For a proton to fuse with a proton, they almost have to literally touch. The electrostatic force on each proton at a distance close enough for fusion is about 13 pounds on each proton. In another simple type of fusion reaction, a proton is fused to a neutron. Neutrons, just like protons, are subjected to the strong nuclear force, which pulls the proton and neutron together. However, since they are neutral and have no electric charge, they are not subjected to any electrostatic repulsion. Because there are no forces which repel a proton and a neutron, it is very easy to bring them close together to initiate a fusion reaction. Let's take a look at some of the simplest atomic nuclei and the forces that are at work within them. First, made up of 1 proton and 1 neutron, is the isotope of hydrogen called deuterium. The only force acting in the nucleus of deuterium is the strong nuclear force, which holds the proton and neutron tightly together. In deuterium, each nucleon, neutron or proton, is bound to only one other nucleon by the strong nuclear force. Now, let's look at another isotope of hydrogen called tritium. Tritium is made up of 1 proton and 2 neutrons. Where in deuterium, each nucleon is held by the strong nuclear force to only one other nucleon, in tritium, each nucleon is held by the strong nuclear force to 2 other nucleons. Because of this, the nucleus is held together with a much stronger force. Next, we look at the helium-4 nucleus, also called an alpha particle, which is made up of 2 protons and 2 neutrons. Since there are 4 nucleons in close proximity, each nucleon is held together by the strong nuclear force to 3 other nucleons. But now we have another force to contend with, which is trying to push the protons apart. That is, the electromagnetic repulsive force. Now, consider a large nucleus made up of dozens of protons and neutrons, and then focus on some of the periphery protons only. Each of these protons attracts each nucleon that is touching it with the strong nuclear force, but only those almost literally touching it. But the electromagnetic force works over much larger distances, and the nucleus of an atom is a very small distance, so these protons repel each other electrostatically with a powerful force. In fact, each proton repels every other proton in the entire nucleus. This introduces a key point critical to the understanding of how nuclei are held together. Every time you add a proton, it repels every other proton, no matter how big the atom is. But the strong nuclear force only pulls together nucleons that are touching it. With the addition of more nucleons, the strength of the electromagnetic forces, which are trying to separate the protons, grows faster than the strong nuclear force, which is trying to hold it together. Larger atoms, then, need more neutrons than protons to help keep them stable. Now that we understand the forces inside atomic nuclei, let's look at all the stellar nucleosynthesis processes in detail. The first chain of reactions is referred to as the Proton Proton chain, which dominates in small to medium-sized stars and makes up the main sequence of these stars. In it, protons are fused into the deuterium isotope of hydrogen, which are then fused into helium. The simplest form of elemental hydrogen is hydrogen 1, whose nuclei is made up of a single isolated proton. As the most abundant element in the universe, about 75% of a star's mass is hydrogen protons. The heat and pressure from the immense gravitational force of the star's mass imparts a large random velocity to protons trapped within the star. This velocity, if high enough, is what enables the protons to overcome their electrostatic repulsion and get close enough for the strong nuclear force to snap them together, initiating fusion, where the star then lights up. Amazingly, though, the temperature and pressure inside the Sun is not hot enough to achieve a proton-proton reaction. The extreme heat and pressure in the core of a medium star like the Sun, while not high enough to initiate proton-proton fusion, nevertheless keeps the protons close enough together that other processes take place which do make it possible. Along with Hans Bethe, Arthur Eddington was a leading proponent of nuclear processes fueling the Sun in order to account for the immense amount of energy it releases. When critics pointed out that the temperature was not hot enough by classical physics standards to account for the proton-proton nuclear fusion, Eddington replied, "I am aware that many critics consider the stars not hot enough. The critics, though, lay themselves open to an obvious retort. We tell them to go find a hotter place." The fact that the Sun was not hot enough to fuse protons caused some confusion among physicists until quantum mechanical processes and nuclear decay revealed what was going on. Quantum physicists showed that subatomic particles need to be thought of as having probable positions, not definite ones, and that their real positions can statistically fluctuate over small areas. They can also tunnel through small energy barriers in an effect called quantum tunneling, in which protons literally disappear and then reappear very close to their original position. Now, the area of influence can be thought of as enlarged because in some cases these protons will disappear and then reappear close enough for the strong nuclear force to overcome the electrostatic repulsive force. It is a rare event, but there are so many protons inside the Sun that billions of these statistically rare events happen every microsecond. Additionally, though, one of these protons needs to undergo a nuclear decay, where it emits a positron, which is like an electron but with a positive charge, and a neutrino, a chargeless particle with almost no mass. Once the proton decays into a neutron, the electrostatic repulsion is no longer present, as the positive charge is carried away in the positron, so now they are able to fuse. The combination of these two events are very rare, and any particular proton might take tens of millions of years before it is close enough to another and one of them undergoes a weak nuclear decay, that they indeed fuse. This is an important reaction because it governs the rate at which stars consume their primary fuel source. In small to medium stars, which are not massive enough or hot enough to initiate proton-proton fusion directly, they may run for billions or tens of billions of years before exhausting their fuel. Large, hot stars run through their proton reaction chains very quickly, sometimes exhausting their fuel in millions of years, an astronomical blink of the eye. This process slows the rate of reaction of small to medium stars. The result of the proton-proton fusion, then, is the hydrogen 2 isotope, deuterium, consisting of one proton and one neutron. The reaction also produces a neutrino, represented by the Greek letter nu, or V. The neutrino is a very small particle without any electrical charge. Energy from this proton-proton fusion comes in the form of kinetic energy of the new deuterium nucleus and kinetic energy of the positron, which rapidly accelerates away from the positively charged proton in the nucleus. That positron will also hit an electron within the star, where an antimatter-matter annihilation takes place, producing a high-energy electromagnetic wave, a gamma ray. All of these contribute to the temperature of the Sun by adding energy to the matter in the Sun. The neutrino, because it is a very small particle and has very little energy, passes right through the entire Sun without interacting. In the proton-proton chain, the actual proton-proton fusion is the hardest fusion reaction to achieve. But as soon as the product of the proton-proton fusion, the isotope deuterium, is present, the rest of the reactions take place rapidly, in the matter of a few minutes. Deuterium fuses with other isolated hydrogen 1 protons. This reaction generates a helium-3 nucleus with 2 protons and 1 neutron, and also generates a gamma ray. At this point, the proton-proton fusion chain can branch in 3 different ways, depending on the mass of the star. The most common branch is the helium-3 fusing with another helium-3 nucleus, generating an alpha particle, or helium-4, plus 2 more protons, which can then be fused again in other reactions. This is the main reaction of stars whose temperature is around 10 million Kelvin to 14 million Kelvin. Our Sun's core is about 15.7 million degrees Kelvin, so about 85% of the reactions at this stage in the proton-proton fusion chain in our Sun are of this type. In stars whose temperatures are 14 million degrees Kelvin to 23 million degrees, the second proton-proton branch dominates. In this reaction, a helium-3 is fused with a helium-4, generating beryllium-7 plus a gamma ray. Because our Sun has a lower core temperature, this makes up about 14% of the reactions at this stage in our Sun's life. Continuing on this branch, beryllium-7 can fuse with a positron creating lithium-7 plus a neutrino. When absorbing a positron, a neutron can turn into a proton. The last stage of this branch sees a lithium-7 fuse with a hydrogen-1 proton, which generates 2 helium-4 nuclei. In large stars that have core temperatures greater than 23 million degrees Kelvin, the third proton-proton branch dominates. In this reaction, helium-3 fuses with helium-4, which generates beryllium-7 plus a gamma ray. This stage is the same as the first stage in the proton-proton branch 2, but the rest are different. Next, beryllium-7 fuses with a hydrogen-1 proton, generating boron-8 plus a gamma ray. The boron-8 nuclei then decays into the beryllium-8 plus a positron, a neutrino, and a gamma ray. The beryllium-8 then decays into 2 helium-4 nuclei. In our Sun, this makes up about 0.1% of reactions. You might have noticed that branch 2 and branch 3 of the proton-proton chains are very similar. Branch 3, though, creates larger elements faster and uses up protons faster. It also creates more neutrinos and helps solve a problem called the solar neutrino problem. 3 of the reactions in branch 3 generate gamma rays. Unlike new nuclei or protons, cannot be reused in more fusion reactions, so reactions which generate them are indicative of processes that use fuel faster. A fourth branch is also possible, where helium-3 fuses directly with a proton, creating helium-4, a positron, and a neutrino. This reaction, however, is hypothesized, and the evidence of it has not yet been observed. Stepping back and looking at stars at a larger scale, consider the formation of a star and the processes involved in its operation. As interstellar clouds of mostly hydrogen and some helium are pulled together by their own gravity, the clouds heat up and start emitting radiation, which slows the rate of the collapse by creating an outward pressure. But if the mass of a cloud is large enough, it collapses into a small, dense sphere which can become hot enough to initiate nuclear fusion. Let's take a close look at the core of a young medium-sized star like our Sun. The early Sun contained about 75% hydrogen in its core and 25% helium. 95% of the life of the Sun will be spent at this stage, burning hydrogen into helium. This is referred to as the main sequence. Our Sun's core today, about halfway through its life, is 30% hydrogen. As you can see here, the proton fusion chain progresses. Individual protons are combined into deuterium, then with another proton into helium-3, and then two helium-3s fuse to create a helium-4. The helium-4 sinks to the center of the core, being a heavier element. So it is about 70% helium and increasing. Over time, all the hydrogen is converted to helium, which the Sun is not hot enough to burn. The core then, at the end of the main sequence, will be mostly helium. Stars are nearly always in a state of hydrostatic equilibrium. The only times they are not is when they are forming and during a supernova explosion. This state is one of a self-correcting feedback. Any change to the system creates an opposing change which tends to counteract the disturbance. For example, if a star experiences a contraction due to gravitational pressure, the resulting collapse creates a greater inward pressure, and thus higher temperatures, and thus more fusion reactions in the core. But more reactions in the core means that more energy is being produced in the core, which raises its temperature, which then creates an outward pressure, which opposes the inward contraction. This outward expansion lowers the pressure in the core, and lowers its temperature, and slows down the reaction rate. Hydrostatic equilibrium is what maintains the star throughout its existence. The two opposing forces of destruction always balancing each other out until there is too much mass or not enough fuel. Some types of stars, such as red dwarfs, are theorized to be able to maintain hydrostatic equilibrium for trillions of years. As a star like our Sun nears the end of its main sequence, it has depleted the core of the easy-to-burn proton fuel supply. When the star depletes its easy-to-burn fuel supply, the hydrostatic equilibrium is out of balance. As the rate of fuel being fused falls below the rate required to retain the internal pressure, the star starts to collapse. Also, since fusion has stopped in the core of the core collapses. As it collapses, the hydrogen around the helium core gets compressed and heated, and it forms a layer around the core, which is itself hot enough for fusion. Since fusion is now taking place in a large spherical shell instead of a small compact core, more energy is conveyed to the body of the star. This expands the outer layers of the star greatly, and thus the star becomes a red giant. Even as a red giant, the star is still fusing hydrogen in a thick band around the core. And as more hydrogen is converted to helium, the core gets denser and collapses further. This heats the hydrogen band more and enables more fusion reactions. The star increases in size still further. The helium core will continue to collapse as more helium is added from the hydrogen fusion layer until the core is hot enough and dense enough for the helium to start fusing. This ends the proton-proton fusion chain, and the star now transitions to the carbon-nitrogen-oxygen cycle characteristic of all large stars. This brings us to the second major fusion cycle in stars, the carbon-nitrogen-oxygen cycle. It dominates during the end sequence of medium stars and during the short main sequence of large stars. The stars have large, dense cores made up of mostly helium, and lighter elements like hydrogen are pushed to the outer layers of the stars. The first major fusion process is the triple alpha process, where 3 alpha particles, helium-4s, are fused to create a carbon-12. The triple alpha process is not common, but it serves as a catalyst for further reactions and sustains the main process of the carbon-nitrogen-oxygen cycle, the CNO1 cycle. This is a complex cycle that starts with the carbon-12 generated from the triple alpha process. It fuses with a proton and emits a gamma ray, creating nitrogen-13, which then fuses with another proton, creating a gamma ray and nitrogen-14. The nitrogen-14 then fuses with another proton, emitting a gamma ray and creating oxygen-15. The oxygen-15 also experiences a proton decay, emitting a neutrino and a positron, turning into nitrogen-15. That nitrogen-15 then fuses, and this is the reaction that creates the most energy in the CNO cycle, with another proton, emitting a helium-4 and resulting in a carbon-12. With that carbon-12, the process can start all over again. The CNO1 cycle essentially uses the carbon-12 nucleus as a catalyst to more protons into helium-4, converting even more of the star's hydrogen fuel into helium. The helium of the core is also getting fused into carbon and oxygen. The carbon-12 fused from the helium facilitates even more of the CNO1 cycles, speeding up the star's consumption of the hydrogen outside the core. The carbon-nitrogen-oxygen cycle, both as complex as the CNO1 cycle, but much rarer, occurring cumulatively less than 0.1% of the time. Now let's take a look at our red giant cross-section again near the core and to the surface. On the right is the helium core. To the left of that is the layer of hydrogen surrounding the core that is now hot enough to fuse. It continues the proton-proton chain, creating more helium and dumping it into the core. The helium core grows and eventually becomes dense enough and hot enough to start fusing helium. This starts the triple alpha and CNO cycle, while the proton fusion chain continues at the outer layer of the helium core. These processes convert more hydrogen to helium-4 and helium-4 into carbon, so a carbon core starts to form as the heavier elements sink to the center of the star. So what happens when the star starts to run out of helium? When our main sequence medium-sized star, our Sun, ran out of hydrogen in its core during the proton-proton fusion cycle, it collapsed and started fusing hydrogen around the helium core. Soon that added enough helium to the core for the core to start fusing helium. Similarly, these processes deposit more and more carbon into the core. The carbon core expands, but it is not able to fuse until the star runs low on helium fuel and again starts to collapse. In large enough stars, this collapse causes the carbon core to start fusing. In the largest stars, this process repeats for each element, all the way up to iron. So here we see a very large star toward the end of its final sequence. As each outer layer runs low on fuel, filling the core with a newer, heavier element, the star's core contracts and starts fusing another new, heavier element. The fusion of lighter elements moves toward the outer layers, which greatly expands the size of the star with each new element. Heavier elements fuse into still heavier ones, but release less energy each time in each new cycle using more fuel. Eventually, an iron core forms and no more energy can be extracted from fusion. And now we've reached the final stage in the synthesis of new elements, the supernova, caused by either the sudden activation or sudden cessation of nuclear fusion, leading to a Type 1 and Type 2 supernova. These vast stellar explosions create the heavy elements in the universe, such as silicon, calcium, titanium, nickel, iron, cobalt, among many others. For short periods of time, the supernova can produce more energy than an entire galaxy of stars do. The Type 2 supernova results from the core collapse of massive stars. In large stars, a successive layer of rings fuses smaller nuclei into continually larger nuclei as the core is approached. The process stops at iron because fusing iron no longer releases energy, so any star hot enough to do so would quickly collapse as it loses the energy required to maintain hydrostatic equilibrium. This is exactly what a Type 2 supernova is. When the iron core reaches 1.44 solar masses, it can no longer support its own weight, and it collapses on itself. As the iron core collapses, it heats up and then fuses into larger elements, but since the core is collapsing, the outer layers of the star also start to collapse. But it's now fusing elements with less binding energy than iron, which takes more energy, which cools the core even more, causing more collapse and more core fusion of larger elements, while the layers of the star continue to collapse under their own momentum now and gravity. Suddenly, the core can collapse no further as it literally becomes a giant atomic nuclei. The rapidly contracting outer layers slam into the now non-compressible core. This initiates more fusion reactions within the collapsing star layers, which imparts energy to the layers. The star layers also rebound off the non-compressible core, like a rubber ball hitting a steel plate. The combination of the rebound momentum and fusion energy explodes the star layers outward. At the same time, a cascading chain reaction within the non-compressible core converts most of the core's protons into neutrons, emitting an intense neutrino pulse. The pulse, even though neutrinos easily pass through matter, convert about 1% of its energy to the now very dense stellar layers, accelerating them still further outward. With the star blown out into space, leaving only a dense core behind. The core is now depleted of protons and made up only of neutrons, making it a neutron star. Larger stars will collapse into black holes. The final heavy elements in the universe are synthesized primarily in one of two ways in the supernova explosion. The first is what is known as the R process, which stands for the rapid neutron capture. In this process, the nucleus of iron or larger elements capture rapidly moving neutrons in the stellar core. But before the nucleus and its extra neutrons have a chance to decay, it is hit by another rapidly moving neutron. So many neutrons are present immediately after the core collapse that in this way larger elements can be formed before the intermediary unstable elements have had a chance to decay. Very large nuclei are formed through this process, which decay into less large nuclei, but still represent the heavy elements. Approximately half of all heavy elements in the universe are formed this way. The rest of the heavy elements are made in the fusion which takes place in the exploding outer layers of the Type 2 supernova. The remnants of these vast explosions are what we see when we look at the inappropriately named planetary nebulae, which are tremendous expanding clouds of stellar remnants. The supernova-fueled explosions of the outer layers achieves the high temperatures needed to fuse the heavy elements, elements which take energy to create. Type 2 supernova are caused when the core of large stars stop fusing and then suddenly collapse. Another type of supernova, the Type 1A, are caused when a fusion reaction suddenly starts and also creates many of the larger elements. In a Type 1A supernova, a collapsed white dwarf or neutron star from a previous collapse of a medium-sized star leaves a dense carbon core which gravitationally steals matter from a companion star in a binary star system. As the core accumulates outer layers of hydrogen from its partner star, eventually enough pressure is built up to suddenly start fusing the carbon core. This causes a series of runaway fusion reactions resulting in another supernova blast, as a large portion of the carbon and oxygen atoms are converted into heavier elements in just a few seconds. This type of supernova is the main source of the lighter, heavier elements, such as iron, nickel, cobalt, and titanium, etc. These are thrown out into space at up to 3% of the speed of light. Here is a great picture of the supernova remnant known as the Helix Nebula, located in Constellation Aquarius. It was a Type II supernova that is about 700 light-years away and 2.5 light-years in diameter. In the center, we see the white dwarf collapsed core. But these odd structures, dubbed cometary knots, are still a mystery. Each one is about the size of our entire solar system. Here is an incredible picture of the supernova remnant, the Cat's Eye Nebula. We see in the center the dense collapsed core, surrounded by concentric rings of exploding material. Closer to the core is the majority of the exploded layers of the original star, still spreading out. We also see these amazing protrusions, which are most likely polar jets undergoing a precession of the collapsed cores. In quick review, the stellar nucleosynthesis process follows these steps. First, in small to medium stars, most of the light elements are fused in the primary fusion chain referred to as the Proton Proton chain. In this chain, hydrogen is converted to helium. Then, in medium to large stars, the heavier of the light elements are fused in their cores, where the carbon-nitrogen-oxygen cycles convert helium to carbon and oxygen. Large stars will fuse carbon up to iron in their cores until the fuel is expended and the star either collapses or explodes in a supernova. Type 1a and Type 1b supernova explosions create the lighter of the heavier elements, while the exploding Type 2 supernova create the rest of the heavier elements when their exploding outer layers sustain runaway fusion reactions, creating larger elements that are manufactured through the rapid neutron capture process known as the R process. What's become clear now is that all elements heavier than hydrogen and helium were fused inside of stars or in their outer layers as they exploded, and subsequently everything we have and are, from the air we breathe and the carbon in our bodies to the steel in our skyscrapers, was forged in the nuclear furnaces of stars. That's why, as Carl Sagan said, we are all star stuff.